Hello everyone, it's a pleasure meeting you in my mathematics class. Today let me try to discuss two problems. One is solving a differential equation with a which is slightly different in the sense that the right hand side function of the differential equation is given as a step function, which is defined as g of t is equal to 1 if t belongs to the half closed open interval 0, 1 and is equal to 0 for t greater than or equal to 1, in the sense that 1 and that y of 0 is equal to 0 and y dash of 0 is equal to 1 using Laplace transform. And the other one is finding the inverse of the inverse Laplace transform of a function. Let me first complete the second problem, then come to the first one if time permits, because of shortage of time. Let me complete the second one now. See, now S divided by S squared plus 4s plus 5 can be written as S by S plus 2 whole square plus 1 square. So this is S plus 2 whole square, making it a perfect square, plus 1 plus 4 will be 5. So this also I will write it for my, so there is a way to do the problem. If you are proficient with this, the algebraic simplifications and also the art of doing a Laplace transform, you will be able to understand what I do here. So this is nothing but S plus 2 minus 2 divided by S plus 2 whole square plus 1 square. This is nothing but S plus 2 divided by S plus 2 whole square plus 1 square minus 2 divided by S plus 2 whole square plus 1 square. Let us keep this. So, the meaning of this is, therefore, your L minus 1 of S e to the power of minus S divided by S square plus 4s plus 5 can be written as it is L minus 1 of e to the power of minus s into, see, I can write this as e to the power of minus s into, in the place of this I can write this as s plus 2 divided by s plus 2 whole square plus 1 square minus 2 divided by s plus 2 whole square plus 1 square. Close this. Now, inverse Laplace transform is linearity property holds good in the case of a Laplace transform. So, I can very well write this as L minus 1 of e to the power of minus s, and it is s plus 2 divided by s plus 2 whole square plus 1 square minus, it is 2 into L minus 1 into within brackets e to the power of minus s, it is 1 divided by s plus 1 whole square plus s plus 2 whole square, and this is what you get. Now you see that when you go for inverse Laplace transform, this e to the power of minus s, e to the power of minus s will make us understand that this is nothing but our step function, which is nothing but u of t minus 1. The inverse of this will be u of t minus 1 into L minus 1 of f of s minus 2 into e to u to the u t minus into this L minus 1 of f of s. Here your s in this, see in this case this is equal to, so this is nothing but u of t minus 1 L minus 1 of, see, s plus 2 divided by s plus 2 whole square plus 1 square minus 2 into u t minus 1 into L minus 1 of, it is 1 by s plus 2 whole square plus 1 square. So this is nothing but, see, this is u of t minus 1 into this is e to the power of minus 2. It is e to the power of minus 2t, but since because of this step function, you see that it will be u e to the power of minus 2t minus 1 into L minus 1 of s divided by s squared plus 1. Likewise, this is minus 2 into u of t minus 1 into, again here it is e to the power of minus 2. It is in the place of step function, because of the step function, e to the power of minus 2t minus 1 into L minus 1 of 1 by s square plus 1 square. But this is nothing but, see, what do you get for this? u into t minus 1 e to the power of minus 2 t minus 1. Now, the inverse Laplace transform of this is cos t. Because of this step function coming, it is defined only in that particular interval. Because of step function, it is defined in a particular interval. So you see that this cos of, it will come as cos of t minus 1, cos of t minus 1 in minus 2 ut minus 1 into e to the power of minus 2t minus 1 into sine t minus 1. So the answer is, so you can take this, it is u t minus 1 into e to the power of minus 2t minus 1 within brackets cos of t minus 1 minus 2 sine of t minus 1. So I will explain this. So I am going to find the inverse Laplace transform of this. Looking at this minus e to the power of minus s, one can understand that this involves a step function. The step function is nothing but u of t minus 1. You see that if you take the inverse Laplace transform of this is u of t minus 1. And then u of t minus 1 into the inverse Laplace transform of the function, namely this one, s divided by s square plus 4s plus 5. But s divided by s square plus 4s plus 5 can be written as s divided by s plus 2 whole square plus 1 square. And this I do some mathematical jugglery here, s plus 2 minus 2, and split it into two fractions, two partial fractions like this. Now you see that the L minus 1 of this is nothing but L minus 1 of this minus L minus 1 of that. Now the inverse Laplace transform of this you can written as e to the power of minus s into sum of, because in this place I can write the equivalent of this is these two I can write. And linearity property holds good in the case of Laplace transform and also in the inverse Laplace transform. So you can split this into two inverse Laplace transforms, namely L minus 1 of e to the power of minus s into this minus 2 into L. You can pull these two outside also in the case of a Laplace transform. or inverse Laplace transform. So minus 2 L minus 1 of in the bracket 1 by this. And when you take the inverse Laplace transform, the inverse Laplace transform e to the power of minus s, the step function namely u of t minus 1 into the inverse Laplace transform of this particular function. Likewise, the same here. You see that here e to the power of minus s will mean that the step function is there. So 2 into u of t minus 1 into L minus 1 of f of s. This f of s is this particular function. Now you see that this is s plus 2. Since s plus 2 comes here, it means that it is e to the power of minus 2t is that. When you take the inverse Laplace transform of that, it is e to the power of minus 2t, but inverse of minus 2t because the step function, it is being defined in a step function. The Laplace transforms or dealt in a, they are step functions. You see that naturally this e to the minus 2 into, in the place of t, we must put it as t minus 1 into the inverse Laplace transform of s by s square plus 1 minus 2 into u of t minus 1, which is a step function, into again it is, you can take this because this plus 2 comes here, it means that e to the power of my inverse Laplace transform will become as what? E to the power of minus 2t, but since it is defined in a step function as a step function, it is minus 2 into t minus 1 into L minus 1 of 1 by s square plus 1 square. Now the inverse Laplace transform of s by s square plus 1 is nothing but cos of t. But cos of t, since it is defined as in a step function in an interval, which is a step function, you see that this should be written as cos of t minus 1. Wherever t comes, you replace it by t minus 1 minus 2 into, you see that write all these things, u of t minus 1 minus 2 into t minus 1 in the bracket, and this is nothing but your sin t. But again, this is the problem is built in a step as a step function, therefore it is sin into t minus 1, and therefore the answer is L minus 1 of, see, L minus 1 of e to the power of minus s into this divided by s square plus 4s plus 5. This is equal to your u into t minus, I take this u of t minus 1 outside, e to the power of minus 2 of t minus 1 in the bracket, I have taken outside, and what is remaining in the bracket is cos of t minus 1 minus 2 sin t minus 1. This is the answer. So this is how we do